Good morning, everyone. Today in this exercise, we're going to study the problem of a rolling sphere down an inclined plane. So we have a bowling ball of mass m and radius r. It rolls without slipping from rest down a ramp inclined at angle theta with the horizontal. We have to determine the acceleration of the center of mass of the ball, the magnitude of the friction force on the ball, the speed of the center of mass of the ball at the bottom of the ramp. And finally, you have to repeat part C. So you have to determine again the speed of the center of mass of the ball, however, using the energy approach and not the approach that you used in parts A, B, and C. So let's move on to the whiteboard. So this is the figure that describes our problem. We have a sphere on an inclined plane. This inclined plane has an altitude h with respect to the horizontal surface, and it makes an angle theta with the horizontal surface as well, as you can see here. This sphere is rolling down, which means that the acceleration of the center of mass of the sphere is it is oriented, or it has this direction, which is downward. And let's take the x and y axis in this way, so that x axis describes the direction of motion, and y-axis is the perpendicular or the normal direction. So we need first, in the first question, the question is in part A, what is the acceleration of the center of mass of the ball? And so in order to determine the acceleration, أفضل طريقة هي إنه نطبق نيوتن second law, right? بس قبل ما نطبق نيوتن second law لحتى نعمل access على acceleration, we have first to discuss what is this motion, and then نحط كل الفورسز acting on this object, وبعدين نطبق نيوتن second law. فأول شيء لحتى نجي نشتغل، شو هو type of motion بهالحالة؟ هو قال لي بالاكسرسايز انه it's rolling without slipping. يعني هون في عنا rolling without slipping motion. It's quite easy to specify لأنه هو قال لي شو هو type of motion. طيب شو يعني rolling without slipping؟ احنا we have seen بالlecture انه rolling without slipping it includes two types of motion. أول شيء في عنا translation of the center of mass of the ball اللي هي بقى of the sphere يعني of the ball. وكمان في عنا الثاني تاني element من هالموشن هي rotation about the axis through center of mass of the ball. So this is why we will have to apply Newton's law. We have to apply Newton's second law on the ball for rotation and for translation. رح نطبق sum of F equals MA والsum of tau equals I alpha. لحتى نجي نطبقهم، فإذا أول step قلناها، ثاني step كمان حددناها، هلا الباقي نحدده هو شو هن ال type of forces that act on this object. طيب خلينا نبلش. هيدي هي السفير اللي عنا إياها and we have basically two forces مبدئيا. أول force هي ال gravitational force, which is the force exerted by the earth on this ball, on the sphere. You have the normal force. The normal force here, the force exerted by the surface on the object. Let's call this N, right? And this is it for the moment, because we don't know what we have next. هلا هو بالاكسرسايز قال لكم انه you have to determine the magnitude of the friction force on the ball. من هون نقدر اول شيء يعني هيدي بحد ذاتها it's a given انه we still have the friction force. بس السؤال هو كيف بدنا نحط الفريكشن فورس وبأي اتجاه and how we are going to specify كمان direction للفريكشن فورس. So let's just make a small discussion. طيب نحن بنعرف انه هذا البول عم تعمل rolling without slipping، يعني عمليا هي عم تعمل rolling، فاذا عم تعمل rotation وترانسليشن. طيب خلينا نطلع على الان والام جي، شو دورهم، شو بيلعبوا دور بهالموشن. both الان والام جي had two forces بيمرقوا بالاكسس اوف روتيشن. لأن احنا بنقلنا بالكورس وهون كتبناها انه the rolling motion can be seen as the rotation of the object about the axis through the center of mass and a translation of the center of mass itself. وبالتالي الروتيشن هون اذا ما نطبق هذا التحليل هو it's about the center of mass. والmg والn, these two forces, they pass through the center of mass, which means that the torque of the normal force as well as the torque of the weight is equal to 0. نحن شفنا انه if a force is passing through the axis of rotation, it produces zero torque. وبالتالي ال N وال mg ما بيلعبوا دور بالروتيشن، ما بيقدروا بيخلقوا rotation about the center of mass, about the axis passing through the center of mass، لانه هن اثنيناتهم مرقين بالcenter of mass. الشيء الوحيد اللي بيقدر يطلع معنا من النتيجه من هيدا السكيم انه ال mg, one of the components of the mg force, it will balance ال n بشكل انه السفير ما تتحرك على الواي اكسس، and this is mg cosine theta هون اللي هون. والكومبوننت الثانيه اللي لها it will cause actually it will cause a sliding motion. يعني الاكس الام جي اكس اللي هي ام جي هون ساين ثيتا، هيدي الفورس رح تخلي السفير to slide down the inclined plane. اما هيدي الفورس اللي هي ام جي كوساين ثيتا فحيكون دورها انه تعادل النورمال فورس بشكل انه السفير ما تتحرك على الواي اكسس. طيب هلا السؤال هو كيف الفريكشن وباي اتجاه؟ حتى نقدر نحدد الفريكشن باي اتجاه لازم نطلع على البوينت اوف كونتاكت ما بين السفير وما بين السيرفيس وشو عم بيصير بهالنقطه تحديدا. طيب نحن قلنا انه الام جي ساين ثيتا under the action of mg sin theta this sphere will slide down the inclined plane. وبالتالي كل البوينتس بهالحاله حيمشوا بنفس اتجاه الفورس، يعني هالبوينت بي حتمشي بهالاتجاه لتحت لانه في عنا سلايدنج، يعني حيكون في عنا ترانسليشن وكل النقاط حيمشوا بنفس الاتجاه باتجاه الام جي ساين ثيتا، وبالتالي النقطه بي كمان حتمشي باتجاه الام جي ساين ثيتا. بس نحن بنعرف انه اذا كان في عنا رولينج without slipping النقطه بي لازم على طول تكون at rest، ما لازم تتحرك بكل لحظه. وبالتالي if we want to discuss كيف الفريكشن فورس لازم تكون، الفريكشن فورس هي the force applied on the sphere على النقطة P بشكل انه تمنعها من انه تتحرك. وبما انه هون ال P عندها tendency انه بتنزل لتحت under the action of mg sin theta، فاذا الفريكشن فورس لازم تكون بالاتجاه المعاكس لهالتندنسي، وبالتالي the friction force should point upward لحتى تعادل هيدا الفيكتور الاخضر اللي هو التندنسي للبوينت بي كيف تمشي، لانه هي رح تمشي لتحت، فالاف رح تكون بعكسها بشكل انه البوينت بي تبقى مكانها to stay motionless and this is it. فبالتالي بنستنتج من هون انه الفريكشن فورس F هي acting on the sphere at the point of contact بالاتجاه المعاكس للتندنسي of motion. وليش في عنا هيدي التندنسي of motion الفيكتور الاخضر؟ لانه الام جي ساين ثيتا هي بهالاتجاه والام جي ساين ثيتا مارقه بالاكسس of rotation، so under this force الاوبجكت حيعمل sliding. And so this is it. Now we have all the forces حطيناهم كلهم على الرسمه، ما باقي علينا غير انه نطبق نيوتن second law for translation and for rotation. And so let's do it. طيب Newton's second law for the translation motion, we know that the sum of F is equal to ma. I'll just take the sum of F on the x-axis، يعني خلينا بس نعمل projection along the x-axis. So شو بيطلع معنا؟ طيب have a look at the figure. ال F هي بعكس اتجاه ال x، فإذا minus F plus mg sin theta is equal to m a center of mass. So minus F plus m times g sin theta is equal to m a center of mass. And so this is the first equation that we can get from the Newton's second law for translation. Now let's apply the second equation اللي هي sum of tau equals I alpha. طيب نحن شفنا قبل شوي قلنا انه التاو النورمال فورس هي ايكوال لزيرو، والتاو للجرافيتيشنال فورس كمان ايكوال لزيرو. ما بقي عندنا غير بس التاو للاف اللي هي different than زيرو، لانه الاف منا مارقه بالاكس اوف روتيشن through the center of mass. والتاو للاف هي اللي عم بتسبب الروتيشن، يعني ما في غيرها بيلعب دور بهيدي الايكويشن تاو sum of tau equals to I alpha. فاذا فينا نحط مباشره انه تاو للاف is equal to I alpha، يعني الدايركشن للالفا اللي بحددها هو التاو اف. اوكي نو خلينا نحدد هلا شو هي الدايركشن بكل الاحوال للتاو اف رقم واحد، ورقم اثنين نشوف شو هي هالتاو. طيب احنا بنعرف انه التاو torque of a given force is equal to the vector position of the point of application of the force, الvector product مع الفورس نفسها. So it's R cross F. كيف بنرسم الR؟ بنوقف على الأكسس of rotation وبننطلق منه بفكتور لحتى ننزل على point of application of the force. So it is like that. So هيدا هو الفector R يلي عم نحكي عنه. Let me just draw it correctly. So this is the vector R we are talking about. Okay? إذا بنجي بنستخدم the right hand rule بيطلع معنا إنه R pointing downward على أول إصبع، ال F pointing upward تاني إصبع، تالت إصبع بيعطينا التاو لبرا. So we end up with, we can deduce that tau of the force, friction force F هي pointing upward، وبالتالي كمان الألفا is pointing upward مثل التاو F. قد إيه قيمتها للتاو F؟ هي عبارة عن ال R الراديوس فإذا تبع السفير مضروب بال F، لأنه إذا بدي أطبق هيدي الريليشن اللي كتبتها فوق، يعني إذا بدي أطبق الريليشن هيدي تاو للF equals للR dot أو cross F هي عبارة عن قيمتها هي direction حددناها، هي قيمة الR ضرب قيمة الF ضرب sin of the angle between the two. بس ما انه الR والF هن perpendicular فاذا الانجل بيناتهم باي اوفر 2 وساين باي اوفر 2 هي 1، فما بيبقى غير الراديوس R مضروبة بالF. اوكي let's put this بقلب الايكويشن، خلينا نكتبها بقلب الايكويشن. فاذا بيطلع معنا انه R dot F multiplied by F is equal to I times alpha. وهي تاني ايكويشن بتطلع معنا من الروتيشنال موشن او من الروتيشنال الايكويشن فور روتيشنال موشن. هلا السؤال هو كالتالي، هون صار في عنا اول ايكويشن فيها F A center of mass وتاني ايكويشن فيها الF والالفا، صار في عنا 3 unknown. We have two equations with 3 unknown. This is not possible. We have to find a solution to evaluate the center of mass, the acceleration of the center of mass من خلال two equations. So there is one important detail what we should never forget about when we are dealing or studying a rolling motion is that in this case we have rolling without slipping. لما نحكي عن rolling without slipping we have seen that the relation between the acceleration and the angular acceleration is given by A center of mass is equal to R times alpha. And so from here we can substitute alpha with the relation A center of mass over R. That's number one. And then don't forget that here the moment of inertia is the moment of inertia of the sphere with respect to the center of mass. لأنه عن جديد نحن لما قلنا أنه الرولينج هو عبارة عن قسمين translation وروتيشن، قلنا أن الروتيشن هي about the axis through the center of mass. So for a sphere we know that the moment of inertia of a sphere with respect to the axis through the center of mass it's given by 2/5 times m times r squared. Okay, so إذا استخدمنا هدول الانبوت two inputs الايكويشن 2 شو بتصير؟ let's call them 1 and 2. then equation 2 بتصير كالشكل التالي f times r is equal to 2/5 m r squared times a center of mass over r. okay طيب now بدنا نختزل r بالنوميريتور والدينومينيتور، كمان r فينا نختزلها من 1 on the other side of the equation. We can reduce it and so we end up with f equals 2/5 times ma center of mass. So this is the third equation that we can get and this equation is quite important. نجي نعمل substitute لل expression of f بالايكويشن 1 بيطلع معنا فإذا 3 and 1 we can deduce the following minus 2/5 m a center of mass. فإذا بنحط محل ال f بنحط قيمتها اللي هي بالايكويشن 3 plus mg sin theta equals لل m a center of mass. okay and now we can كمان already we can reduce the factor m بكل المحلات. بقي بقى نجمع ال a center of mass 1 plus 2/5 بيطلع معنا 7 over 5. So we end up with 7/5 a center of mass is equal to g sin theta. And so finally we can deduce that a center of mass is equal to 5/7 G sine theta. And this is it. So this is the answer we are looking for. The acceleration of the center of mass of the ball is given by 5/7 times G times sine theta. Let's move on to the second part now. So in part B, the question was, what is the magnitude of the friction force acting on the ball? From equation 3, actually, we can simply write down that F is equal to 2/5 times m multiplied by the acceleration of the center of mass. And all what we need to do is to substitute the acceleration of the center of mass with its expression, which is 5/7 times G times sine theta. So إذا إجا هون بنجي بنختزل ال 5 on both sides, we end up with F equals to 2/7 times mg sine theta. This is it. In part C, we are asked about how much is the speed of the center of mass of the ball after it has rolled down the incline until the end. يعني كانت بأول position فوق ونزلت وصلت لتحت. So this is it. Initially كانت السفير هون بهالنقطة وصلت لهون. Okay? So from this point to this point. من هذا النقطة لهالنقطة، علما انه ال vertical distance يلي مشيتها عمليا هي h. Okay? Now بما انه هو قالنا بالبارت دي انه you have to calculate the speed of the center of mass of the ball using the energy approach، معناتها انه بهيدي البارت ما فينا نستخدم الانرجي approach، لازم نلاقي طريقة ثانية. لازم نلاقي طريقة ثانية علما انه لازم نشوف شو عندنا معطيات، يعني نحن شو بنعرف هلا صرنا على السفير؟ طيب صرنا بنعرف شو هي الاكسلريشن اوف ذا سفير، ال A center of mass which points downward. بنعرف شو هي الفريكشن فورس، بس الفريكشن فورس ما كثير حتكون مفيده لنا at this stage. اهم شيء الاكسلريشن. Acceleration is given by 5/7 g sine theta. So have a look. 5/7 is a number, so of course it's constant. G is constant and theta is constant, which means that in this case we are dealing with an object which is moving under a constant acceleration. A center of mass is equal to a constant. And we know that this sphere was released on the top of the inclined plane, and then it arrives at this point with a given speed for its center of mass. So we can apply actually the equation which is given by one of the equations that we have derived for a uniformly accelerated rectilinear motion اللي هي v final squared minus v initial squared is equal to 2a y minus y final, or x minus x final. Okay, 2a x minus x final. Now if we want to apply it at our case، طيب ال v final ما بنعرف، احنا هلا عم ندور عليها اللي هي سميناها v center of mass squared. ال initial value of the velocity هي عبارة عن 0 لأنه it was released from rest. That is equal to طيب 2 times the acceleration of the center of mass, right? Multiplied by اللي عم ندور عليها هي delta x، هي x oops it's x final minus x0 here. So it's x final minus x0. Let's call x final minus x0, let's call it delta x, okay? And let's have a look here at this figure. So من هالفيجر شو في عنا؟ هي delta x. Look, this is delta x. This is h, and this is the angle theta. So we can immediately deduce that from sine theta is equal to h over delta x. So we can deduce that h is equal to so delta x, pardon, احنا h معنا اياها as a given. We need delta x, so delta x is equal to h over sine theta. And so now all what we need to do انه نحط كل شيء بقيمته. So it's 2 multiplied by a center of mass is given by 5/7 times g sine theta multiplied by delta x هي equal h divided by sine theta. هلا بما انه الثيتا is different than 0 and also is different than pi، هي عبارة عن angle ما بين الزيرو وما بين الباي فالساين ثيتا هي different than zero and so it cancels out between the numerator and the denominator فبيطلع معنا انه VCM squared is equal to 10 over 7 times G times H. And so we can deduce that the speed of the center of mass at the end of the ramp is given by square root of 10 GH over 7. هيدا هو الجواب اللي بيطلع معنا from this method. And so this is it. This is how we can determine the speed of the center of mass of the ball after it has rolled down the total inclined plane. Now the last part is about the same question, what is the speed of the center of mass of this ball, but not using this approach, but instead using the energy approach. So using the energy approach, we are going to use the principle of conservation of the mechanical energy of the ball. لأنه يلي صار when it was on the top بهالposition فوق ونزلت على البوزيشن لتحت يلي صار انه صار في variation of the gravitational potential energy للسفير خسرت potential energy وتحولت ل kinetic energy. And so we have conservation of the mechanical energy. Now إذا عم تسألوا حالكم كيف في عنا conservation of mechanical energy and we have a conservative a non-conservative force acting in the system اللي هو ال friction force. Actually, this frictional force, it does not transfer any energy to thermal energy between the ball and the surface. لأنه البول ما عم تعمل slipping. فبالتالي ما بيصير في خسارة للميكانيكال energy and it's not transferred as thermal energy. لأنه الفريكشن فورس اللي عم تعمل action على هالسفير هي static. And the point P is not moving. So this is why F ما عم تعمل ولا أي work. The work of the frictional force is zero, and we can apply the conservation of the mechanical energy on the ball. So we can write down then the mechanical energy in the initial state is equal to the mechanical energy in the final state, or at initial time and at the final time. So K initial plus U initial is equal to K final plus U final. Okay, now if we put each term with its value. So first of all, the kinetic energy in the initial position is zero because the ball was at rest. The gravitational potential energy in the last position أو الآخر position لما نزلت لتحت كمان كانت zero if we take it to be our reference for the gravitational potential energy. يبقى عنا إنه at the initial time كان في عندها gravitational potential energy هي mgh يعني كانت على ارتفاع h من reference level. يعني إذا ما نجي نحط هون بهالشكل هيدا هون كانت بالinitial state هون كانت بالفاينل state. اوكي اذا اخذنا هيدا level to be our reference for the gravitational potential energy وعلما انه هيدي هي ال h, so this is our reference for the gravitational potential energy. Then we can write down انه بالinitial state كان عندها mgh, right, and for the gravitational potential energy, and in the final state ما كان في عندها غير بس kinetic energy اللي هي عبارة عن 1 over 2 m times v center of mass squared اللي هي it's coming from the translation part of the motion. But don't forget that in this case you also have rotational motion and you have a kinetic energy term associated with the rotational motion, so it's half I center of mass times omega squared. But since here we are dealing with a rolling without slipping motion, we know that in the case of rolling without slipping, omega or V center of mass is equal to R times omega, where R is the radius of the sphere. And so we can write down M times G times H is equal to 1 over 2 M V center of mass squared plus, so 1 over 2 times the moment of inertia of the sphere with respect to its center of mass, it's given by 2 over 5 times mr squared multiplied by omega squared is given by V center of mass squared over R squared. وهلا فينا نعمل كل الاختزالات الممكنة. So first of all, let's start R squared and R squared, they cancel out, and then we have M التيرم موجود صار بكل ال elements بهالايكويشن، كمان فينا نختزلهم. So بيطلع معنا GH is equal to 1 over 2 plus 1 over 5. So we end up with 7 1 over 2 plus 1 over 5. So we end up with, no, not 7. We end up with 7 over 10 times V center of mass squared. And so we can finally deduce that the speed of the center of mass at the end is given by 10 over 7 GH. وبما انه في عندنا square root squared نحط square root. And so we deduce that the speed is given by square root of 10 over 7 times GH, which is, I mean, unsurprisingly, it's exactly the same as we had earlier with the part C. هي عبارة عن square root of 10 over 7 times GH. So whether using the energy approach or using the kinematic equations, given that the acceleration is a constant, you end up with the same value. So this is it for this problem. So in this problem, we are going to discuss the motion of a yo-yo. A yo-yo is made of two identical discs, each of mass m and radius r, attached at their centers to a massless cylindrical axle which has a smaller radius b. So each of these discs on the outer part اللي هن من برا بيجوا عنده radius small r, والaxle it has a radius small b. Now a string is attached to and wrapped around this axle. So في عنا string جاي مبرومة حوالي هيدا الأكسل. After it is released, the yo-yo rolls down its string a distance h. Determine the acceleration of the center of mass of the yo-yo, the tension in the string, the speed of the center of mass of the yo-yo after rolling through distance h. So we're going to discuss this case اللي هي اليو-يو and then answer the questions. Let me move to the whiteboard. So in this picture here, you can see two figures. The first one, it shows how this yo-yo is made of. So we have أول هون عندكم أول circular plate وثاني circular plate, which are, you can think of them as discs, right? And the axle in between, هذا الأكسل اللي بيربط بيناتهم. وهذا الخيط يلي مربوط حوالي الاكسل بشكل انه بس نفلته اليو-يو حيبرم حوالي هذا الخيط، الخيط حيفك عنه. Now اذا بنوقف نطلع من هي الجهه, so this is the side view. If you look from this side بصير في عندكم الفرونت فيو، حتلاقوا انه في عندكم سيركل كبير هو حيكون يمثل الديسك او يمثل البليت، سيركلر بليت البرانيه، وهيدا السيركل الصغير حيكون عم يمثل الاكسل. And this point is the center, it's the point or the axis through which this object is making rotation. طيب now الفكرة هي هلا when this object is released, it rolls down a distance which is given by h, where h is the vertical distance ما بين الانيشال والفاينل position. We have to find the acceleration A of the center of mass, the tension in the string, and the speed after it has traveled this distance h. So again, we have to first of all discuss the motion. What is the type of the motion? What Newton's law to apply, and then draw all the forces acting on the object. So let's start first by the type of motion. In this case, we have an object that is rolling. Type of motion, we are dealing with a rolling without slipping. Rolling without slipping, because in this case, the string is not slipping. ما عم بزحط الخيط، وعقد ما عم يبرم الخيط، عقد ما عم بفك الخيط عن الأكسل، عقد ما الcenter of mass لهاليو-يو عم يمشي. So we are in the case of rolling without slipping in the sense that this yo-yo, it displays both a downwards linear motion of the center of mass, of its center of mass, downward linear motion, and also it's displaying a circular motion about the axle. So we are in the case where we have both a combined أو بالأحرى a combined motion between translation من أول وحدة و rotation من تاني وحدة. لنفس الوقت الخيط عم بفك، الcenter of mass عم يمشي نزول بهالاتجاه هيدا. Now So we know what we are dealing with. Now the second step would be to apply Newton's second law. And Newton's second law will be applied for both cases, for translation and rotation. So let's apply Newton's second law for both translation and rotation. And before to do so, before to start with it and rotation, خلينا نشوف شو هن forces that are acting on this system. Now, we have أول شيء, obviously you have the weight. This is the force acting on this object, and it's pointing downward لأنه this force exerted by the earth on this yo-yo. So I will just call it mg, okay, where m is the mass of the yo-yo. And then you have the only other force that is acting on this object, heat tension in the string. So this is the other force اللي هي T. And of course, it points out upward in the direction and along the string. هي على الstring. Okay, so this is it. These are the forces acting on this yo-yo. All what we need to do now is just to write down Newton's second law for translation and for rotation. And for this reason, let's specify the direction of the acceleration of the center of mass. فهون اليو-يو عم ينزل بنفس الوقت اللي عم يبرم. So the acceleration of the center of mass points downward. هيدي هي A center of mass, right? And so this is it. Let's write down. So for translation, Newton's second law is given by sum of external forces is equal to the mass times the acceleration, where here we are dealing with the acceleration of the center of mass. So هون ما رح احط A center of mass كل مرة. I will just keep it A. Okay, بس نحن بنعرف انه we are dealing with the acceleration of the center of mass. So we can write down T plus mg is equal to ma. Okay, now if we make the projection رح ناخذ the direction of A to be the direction, the positive direction, فهيطلع معنا minus T plus the mass of the yo-yo. هو قالوا لنا انه هاليو-يو it's composed of three parts: two circular plates of mass small m plus an axle of negligible mass. فاذا نحط الام capital M equal ل 2m لانه هي الماس لليو-يو هي الماس ل 2 discs plus the mass of the axle, which is 0. So plus 2mg is equal to 2ma. And so from here we can deduce that T is given by 2m times g minus a, where again a is the acceleration of the center of mass. هي أول equation طلعناها من خلال Newton's second law applied on the yo-yo for translational motion. Now for the rotational motion we have to do exactly the same. So sum of tau is equal to I times alpha. Okay, so we end up with the only force that is making a torque or producing a non-zero torque هي tension. لأنه tension موجودة على بعد أول شيء from the axis of rotation. This is the position, this is the point of application of the force T, and here are the vector position of the point of application of this force. وبالتالي T is the only force producing a non-zero torque. mg مرقة بالاكسس of rotation، فاذا التورك تبعها هو صفر. واذا نقدر نكتب فاذا T تاو للT اللي هو is given by T multiplied by the radius، والradius بهالحالة هو عبارة عن small r، هو they called it B, so I'll just call it B. T times B, okay, that is equal to I times alpha. So I, the moment of inertia of the yo-yo with respect to its center of mass, right, multiplied by alpha. Now, how much is I center of mass? طيب خلينا نحطها. اليو-يو is composed of two discs or two circular plates plus the axle. So I center of mass is expected to be the moment of inertia of the axle plus 2 times the moment of inertia of the plates, which we are going to call them discs. Okay. الآي للأكسل هي صفر لأنه الأكسل is massless. So this is going to be 0. ما عنده mass. أما الآي للديسك with respect to the center of mass يلي لها هي عبارة عن 1 over 2 times m times r squared. So m is the mass of the circular plates عندهم mass small m and radius small r. So half mr squared multiplied by 2. And so we end up with m times r squared. Okay, so we can write down finally that t times b is equal to mr squared multiplied by alpha. بس الالفا already هي عبارة عن شو؟ الالفا هي we can actually connect alpha with the angular acceleration with the linear acceleration. ليش؟ نحن هون عم بيصير في عندنا rolling without slipping. بس وين السليبنج اذا بده يصير حيصير على هالنقطه اللي هي النقطه ما بين السترينج وما بين الاكسل. because this is where the tension is. والتنشن هي الفورس اللي عم تعمل عم تسبب الروتيشن بمعنى او باخر، لانه هي التورك تبعها هي اللي different than zero. فاذا on this point we should not have any slipping, which is the case. فبالتالي we can write down انه the acceleration of the center of mass is equal to the radius multiplied by alpha. بس which radius؟ radius يلي عليه عم بيصير فيه الفورس اللي عم بتسبب او عم بتكون محرك للروتيشن اللي هي التي. فاذا it's about the distance b. هيدا الراديوس الصغير هو سميناه هون بي على الرسم كان مسمى، والراديوس الكبير كان اسمه r. So A center of mass is equal to B multiplied by alpha. فإذا الألفا هي A divided by B. So mr squared times A over B. And so from here we can write down that the tension T هي mr squared over B squared multiplied by A, where A is the acceleration of the center of mass. So this is the second equation that we can deduce from the Newton's second law when applied on this yo-yo for its rotational motion. And now if we can just combine the equations 1 and 2, we can eliminate the tension and we can access and deduce the expression for the acceleration. So let's do it. Now equations 1 and 2 we can write down. so T أول equation T is equal to 2mg minus A. محل T رح نحط قيمتها. فإذا m r squared over b squared times A, that is equal to 2mg minus A. Right? So let's actually get rid of the mass term. بروح بيبقى عنا so if we divide by 2, if we divide by 2 فينا نشيل هون ال 2 بنقسم هون على 2. فبصير في عنا 1 plus r squared over 2b squared multiplied by A is equal to g. And so from here we can deduce that A, the acceleration of the center of mass, is given by g divided by 1 plus r squared over 2b squared. And this would be the acceleration of the center of mass of the yo-yo if we describe the yo-yo as an object which has two uniform circular plates and an axle in the middle. فاذا هيدي بالنسبه للاكسلريشن جبناها. بتاني بارت كان مطلوب منا نجيب شو هي التنشن in the string. بما انه جبنا الاكسلريشن we can immediately deduce that the tension in the string from equation 2 is given by mr squared over b squared multiplied by A يلي هي g divided by 1 plus r squared over 2b squared. So we end up with بيطلع معنا ال T هي عبارة عن so let me now do it. في عنا ال mg من فوق نخليهم مثل ما هن، وتحت فينا نقسم على فينا نضرب كل هيدي ب b squared over r squared. So we end up with 2 plus b squared over r squared. This is the tension in the string. And then finally, in the last part, we were asked about the speed of the center of mass of the yo-yo after it has rolled through a distance h. بما انه acceleration هون again it's a constant value. It has a constant value. G is constant. The radius of the discs or the plates is constant, and the radius of the axle is constant. So since A is constant, we can apply the kinematic equations for a uniformly accelerated rectilinear motion. And so we can write down v squared minus v0 squared is equal to 2 times a y minus y0. So 2a delta y. Now, in the initial time the yo-yo was at rest, it was released, so v0 is equal to 0. Y minus y0, this is nothing else than the vertical distance h through which the yo-yo has rolled. And so we end up with v squared is equal to 2 times a هي عبارة عن g over 1 plus r squared over 2b squared multiplied by h, and so it's given by 2gh over 1 plus r squared divided by 2b squared. Now, if we want to deduce how much is v, we can simply take the square root. بيطلع معنا ال v هي square root ل 2gh divided by 1 plus r squared over 2b squared, and this would be the answer for the speed of the center of mass after the yo-yo has rolled through a distance h. Now, a side comment is that we can also, in this case, apply the energy approach to in order to deduce the speed of the center of mass by using the principle of conservation of mechanical energy. Because there is no slipping in this system of mechanical energy of the yo-yo, we can then write down that the mechanical energy at the initial moment is equal to the mechanical energy at the final moment. And so therefore, K initial plus U initial is equal to K final plus U final. Now, if we take the final position to be our reference for the gravitational potential energy, this becomes 0. And in the initial time, it was released, so K initial is equal to 0. So we end up with the mass of the yo-yo, اللي هي 2m times g times h, لأنه اليو-يو كان على ارتفاع h من الفاينل position in the initial position is equal to the kinetic energy. The kinetic energy هي عبارة عن kinetic energy of translation and of rotation. ليش؟ لأنه اليو-يو عم يعمل rolling. So it's half I center of mass omega squared plus half times m اللي هي الماس of the yo-yo اللي هي 2 times m multiplied by the speed of the center of mass squared. Now again we have to replace I center of mass with its value. نحن جبنا قبل انه ال I center of mass لليو-يو هي عبارة عن mr squared. You remember that was in here. So I center of mass is equal to m times r squared. So if we replace this with mr squared, we end up with mr squared multiplied by الأوميجا هي ال V center of mass divided by R, right? بس بما انه هون كمان الرولينج عم بيصير حوالي الاكسل, so this omega is nothing else than V center of mass divided by B. And if it is squared, then both are squared plus half times 2m times V center of mass squared. Now all what we need to do is to make some cleaning للإيكويشن. فشو بيطلع معنا؟ خلينا نكتب تحت 2m G and H. And so we end up with, let's actually خلينا نشيل ال m, let's reduce the m factor everywhere. So this is reduced now, and هون 2 with 2 also they are reduced, and so we end up with 2gh is equal to, نحط V center of mass in factor بيطلع معنا 1 plus r squared over 2b squared multiplied by V center of mass squared. And so we can finally deduce that the speed of the center of mass is given by square root of 2gh over 1 plus r squared over 2b squared. And this would be the result, which is exactly the same as what we get from the kinematic equation اللي استعملناها when A is equal to a constant. It's exactly the same result, and this is of course not surprising. We should have the same result at the end of the day. So this is it for the yo-yo. A new problem in chapter 10. So as you can see in this figure, you have a cylinder, which we call C, of mass capital M and radius capital R, is attached to a block B, which has the same mass, through an extensible and massless cord that passes over the pulley that you can see in the figure. And this pulley has the form of a disc, which has a mass capital M and radius small r, which is equal to capital R over 2. The cylinder rolls smoothly, which means without slipping, over a horizontal table, and the cord doesn't slip over the pulley. The questions are like that. So first of all, what are the nature and the direction of the friction force between the cylinder and the table? So this is the same kind of discussion that we have done in the previous exercises. You have to find the acceleration A of the block as a function of g, deduce the tensions in the string T1 and T2 in terms of M and G, where T1, as you can see in the figure, is is the tension in the string between the pulley and the cylinder, and T2 is that between the pulley and the block. And finally, use the conservation energy approach to find the speed of the block B after it descends a distance d. So this is it. Those are the problems. Now, in the given, the moment of inertia of the cylinder or disc, because both have the same actually moment of inertia, about an axis perpendicular to it and passing through its center of mass is given by I center of mass is equal to 1/2 times mr squared. Where m is the mass of the object. So if you are talking about the cylinder, it's the mass of the cylinder times the radius of the cylinder squared. And if we're talking about the disk, then it's the mass of the disk times the radius of the disk squared. Let's solve this problem. And so for that reason, let's move to the whiteboard. So this is our figure. Here you have the cylinder, and here is the block, and the pulley is the bridge between the two, because the cord, it passes through the pulley. So as long as this object, this block, is descending, then the pulley will move on the table, and it will move as a rolling motion, rolling without slipping motion. Now let's start with the questions. The first question is, determine the nature and the direction of the frictional force F between the cylinder and the table, and justify your answer. So why it's going to be in one direction and not in the other, for example. Okay, so when we are talking about the friction force, then we're talking about the cylinder motion, and this is why we have to look at the cylinder, what's going on. So what are the forces acting on the cylinder? Basically, we have the weight given as mg, and we have the normal force exerted by the table on the cylinder. So this is the normal force N. And we have the tension T1 in the string. Now, if we make a study of what happens to the cylinder when all these forces are acting on it, you'll find that N will mg, they will counterbalance each other in such a way that the cylinder will not move along the vertical direction. فال N will mg مع بعضهم, they cancel each other along the y-axis. T1 is the only force that is acting in the x direction. إذا بناخد هيدا to be the x direction and this to be our y direction. So let's say this is x and this is y. Along the x-axis we have only T1. بما انه ال N, ال mg وال T1 كلهم بيمرقوا بالاكسس of rotation through the center of mass, ثلاثتهم ما بيسببوا ولا اي تورك. فلهالسبب الفورس الوحيده اللي بتقدر تسبب موشن هي T1, and it's going to be a translational motion. So if you look at the points, and in particular at the point P in here, اللي هي نقطه الكونتاكت ما بين التيبل وما بين السيلندر, you'll find that this point will have a tendency to move to the right? لأنه T1 هي it's oriented to the right. T1 will not produce any rotation, it only produces a translation. فالpoint P of contact حتمشي لقدام. Then if we will have rolling without slipping, لازم يكون في friction force ما بين السلندر وما بين السيرفس بشكل انه النقطة P تضل at rest. إذا بدنا النقطة P تضل at rest لازم الفريكشن فورس تعاكس tendency للpoint P انه تتحرك. ما انه البوينت بي عندها تندنسي انه تتحرك باتجاه اليمين، فاذا الفريكشن فورس لازم تكون باتجاه الشمال. واكيد هيدي الفريكشن فورس is going to be a static friction force because we want the point P to remain at rest, not to move at all. So we are dealing with a static friction force. So let's write down that. So first of all, in what concerns the nature of the friction force, we are dealing with a static friction force. In this case, that's number one. And in what direction it is oriented, so we can say that F directs towards or to the right, to the left, to oppose the tendency of the contact point P between, the contact point between the cylinder, and the table point to slide to the right. And so هدفنا انه النقطة بي تضلها at rest، تضلها مكانها لحتى يصير في rolling without slipping. ورا هالسبب لازم الاف تكون فاذا مثل ما قلنا باتجاه الشمال. So بهالطريقة صار في عنا كل الforces that are acting on the cylinder. This is the first question. Now, the second question was part B. You have to find the acceleration A of the block in terms of G. So now let's have a look at the block. هالبلوك عم ينزل and the block is moving downward. It travels a distance downward, and let's call A the acceleration of the block. So if the block has moved downward through a given acceleration A, and the fact that the chord is inextensible and it's massless, then as long as the block will move, the sphere also will move on the horizontal axis. And so both of these objects they will move with the same acceleration. So the acceleration of the cylinder is equal to the acceleration of the block is equal to A. In order to access A مثل ما بنعرف, we have to apply Newton's second law. The only thing is that here we have three objects to deal with. في عنا البلوك اللي عم يمشي باتجاه نزول. في عنا السلندر يلي بحكم انه هو مربوط بالبلوك through the cord كمان عم يمشي باتجاه اليمين. وفي عنا كمان اضافه لهم هي البولي، لانه in this case the pulley is considered as a disc of mass capital M and radius R over 2. So the pulley isn't massless as we have seen in previous chapters, and so we have also to consider the motion of the pulley and apply Newton's second law on these three objects. So let's start one by one. Okay. First of all, let's start with the block. So we have, in order to determine A, we need to apply Newton's second law on the block B, on the cylinder C, as well as on the pulley P. Okay. So let's start first with the block. On the block, طيب بالنسبة للبلوك شو في يعني؟ رح ارسمه هون على جنب. What are the forces acting on the block? So we have the weight of the block. البلوك عنده mass capital M مثله مثل السيلندر. So its weight هو عمليا عبارة عن M times G اتجاه نزول. We have the tension in the string اللي هي T2 also acting on this block. And this is it. And we have the acceleration of the block. A is pointing downward. So here its acceleration. Now, all what we need to do is to apply Newton's second law. Sum of external forces along the y-axis is equal to M times AY. Let's stick to the X and Y direction as we have chosen them in this figure in here. يعني X to the right and Y upward. فبيطلع معنا plus T2 minus mg is equal to minus MA. لأنه ال A بهالحالة pointing downward while the positive direction of the y-axis is upward, so minus MA. And so we can write down من هون minus T2 plus mg بس حقله بالماينس sign وخلي ال A positively oriented. So minus T2 plus mg is equal to M times A. And so this is the first equation that we get from the Newton's second law applied on the block. Now let's move on and apply Newton's second law on the cylinder, okay? So on the cylinder, what do we have? So in the same way, I will draw the cylinder هون على جنبنا لحتى بس نشوف كل شيء على الرسمة قبالنا. This is our cylinder, and this is the kind of support من خلاله السلندر معلق بالكيبل. And مجموعة الفورس اللي عم يعملوا اكشن عليه هن بالشكل التالي. So this is T1. This is the weight mg acting on its center of mass. We have the normal, I'll call it just N, we called it N. وفي عنا الforce of friction, static friction F, اللي هي pointing to the left, and it is applied at the point of contact between the cylinder and the surface. And now, since the cylinder is undergoing two motions, هو عبارة عن rolling without slipping. يعني هو عبارة عن translation of the center of mass and rotation motion about the axis through the center of mass. So we have to apply Newton's second law for these two type of motions. So first of all, بهالحالة, let's apply the translational version of Newton's second law. Sum of F is equal to ma. Okay, I'll call it just fx and ax to say that we are dealing only with the x direction, heat direction of motion. Don't forget that in this case, the acceleration of the cylinder, it has the same magnitude as the acceleration of the block, but it has different directions. So let me remove here. هذه هي acceleration للcylinder. So we end up with minus f, right, plus t1 is equal to the mass of the cylinder here, capital M and A. So minus F plus T1 is equal to MA. And so this is, I will just call it equation 2. هلا تاني equation اللي ممكن يطلع معنا هي من خلال Newton's second law on the translational motion لcylinder. So sum of tau is equal to I alpha. And don't forget that here, the I اللي عم نحكي عنها هي the moment of inertia with respect to the center of mass. So I'll just put I center of mass and then alpha. بما أنه كل الforces they pass through the axis of rotation except the friction, فبنقدر نكتب فإذا إنه tau للفريكشن هي equal ل I center of mass alpha. And what is the tau of the friction? So in terms of direction, لازم نمد ال vector position of the point of application of the force. هاي هي ال point of application of the force محل ما حطيتها بالأخضر، هي ال point of contact ما بين ال object السلندر وما بين التيبل. ال vector position of this point هي ال vector اللي بيمتد من ال axis of rotation لعنده. So this is R. And so we know that tau F is given by, so tau F is equal to the vector R cross F. Okay? If you use your right hand, the right hand rule, and using your right hand, you will end up with tau pointing inward. So عمليا بيطلع معكم إن tau للفورس F friction هي لجوا. وطبعا the direction of alpha is defined by the direction of tau F لأنه ال F هي الوحيدة اللي عم تعمل torque about the axis passing through its center of mass. Now, how much is the magnitude of this tau F? الماجنتيود لها هي الماجنتيود لها الكروس برودكت، وبالتالي هي الماجنتيود للR مضروبة بالماجنتيود للF مضروبة ب sine of the angle between the two، بما إنه هول they are perpendicular. So sine pi over 2 is equal to 1, and tau F is equal to the radius of the cylinder بهالحالة اللي هو الR مضروبة بالF. Okay. Now we put this back into the equation. بيطلع معنا إنه الR مضروبة بالF is equal to. Now, the moment of inertia of the cylinder about an axis passing through its center of mass perpendicular to it حسب الجيفن هي عبارة عن 1 over 2 times m mass of the cylinder radius of the cylinder squared multiplied by الألفا اللي هي angular acceleration. This is nothing else than a over r. لأنه إحنا بنعرف من condition of rolling without slipping إنه the acceleration is related to the angular acceleration through the relation A equals to R alpha, right? And so now we can deduce نعمل simplification again. الR مع الR بتروح والR اللي هون مع الR يلي تنتين جهة كمانها بتروح. And so we end up with one equation that is given by F that is equal to half times MA. Okay, so this is another equation. It's equation 3, let's call it. And we have one more equation, final equation. اللي هي جاية من Newton's second law applied on the pulley. So let's see what happens on the pulley. In this case, we don't neglect the mass of the pulley. And so the pulley is making or undergoing a rotational motion. لأنه اللي عم بيصير هون على البولي there is a string that is wound around it. Okay. وبالتالي في عنا tension من الجهتين. فمن جهة السيلندر في عنا tension T1 بهالاتجاه هيدا، ومن جهة البلوك في عنا tension T2 بالاتجاه المعاكس. And of course both T1 and T2 they are tangential to the to the disk اللي هي البولي هي عبارة عن disk بهالحال. Now of course this is the center of the pulley. And since it's undergoing a rotational motion, and if you apply Newton's second law on the pulley, you will end up with some tau is equal to I of the pulley about the axis passing through its center of mass times alpha. لأنه هيدي هي الروتيشن عم بتصير حوالي الأكسس passing through the center of mass. Now we can write down then T1 plus tau 1 plus tau 2 to say it's tau of the first, let me just draw this like that. So tau 1 of the tension T1 plus tau 2 of the tension T2 is equal to I center of mass times alpha. And now let's specify the directions of both T1 and T2, tau 1 and tau 2. طيب بالنسبة ل T1, the point of application of T1 هي هون. The point of application of T2 رح حتى مباشرة هي هون. And so the vector position of the point of application of T1 هي R1. I'll call it R1. And the point of application of T2 it has a vector position R2. مثل ما نكون شايفين هي ال R2 هذيك هي ال R1. Now all what we need to do is to use the right hand rule to determine the directions of tau 1 and tau 2. So you can use the right hand rule and you'll find that tau 1 points upward, tau 1 لبرا, أما tau 2 لجوا. بس كيف اتجاه دوران البولي اتجاه دورانها clockwise مثل عقارب الساعة. فبالتالي الالفا is pointing inward مثل التau 2. Okay, and so now if we take direction للالفا to be the positive direction, بهالحالة رح يطلع معنا إنه minus tau 1 plus tau 2 is equal to I alpha. شو قيمة التاو 1 والتاو 2؟ قيمة التاو 1 والتاو 2 فإذا minus T1 times R, where R is the radius of the pulley, plus T2 R is equal to ال I center of mass so I will just write down immediately. The I center of mass للpulley هي عبارة عن 1 over 2 mr squared, where m is the mass of the pulley and r is the radius of the pulley squared. هيدي الاي سنتر اوف ماس مضروبه ب الاكسلريشن البولي والبلوك والسلندر ثلاثتهم عم يمروا بنفس الاكسلريشن اللي هي A. عم كانوا عم يتحركوا بنفس الاكسلريشن بحكم انه في عندنا inextensible massless cord يلي عم تربطهم ببعضهم. and بما انه الكورد it's not slipping معناتها انه هون البولي عم تبرم على قد ما البلوك عم يمشي. And so this is why alpha is related to the linear acceleration through the equation A over R. يعني the rim of the pulley هي it's moving in the same way as the block. So the tangential acceleration of the point on the rim is equal to the acceleration of the block, with tangential acceleration للpoint on the rim هي equal to R times alpha, where R is the radius. فهون بهالحالة بيطلع معنا T2 minus T1 okay is equal to, just we can remove those two, is equal to R squared مع R والR من تاني جهة بيروحوا بيبقى عندنا 1 over 2 times M times A. So this is the third equation or the fourth equation that we can get from Newton's second law when we applied on the pulley. بيطلع معنا هي مجموعة equations اللي صاروا معنا. So again you can see from the Newton's second law applied on the block we end up with equation 1 where we have T2 and A as unknown. From the cylinder we get two equations. أول وحدة من translation وتاني وحدة من rotation بحكم إنه السلندر عم يعمل rolling motion, rolling without slipping of course. And finally لما نطبق Newton's second law على البولي كمان بيطلع معنا another equation which includes T2, T1 and A as the unknown. Now the point in this question is to determine what is the value of the acceleration. So what is A? لهالسبب رح نشوف شو ممكن نعمل. So look, have a look. بالايكويشن 1 في عنا minus T2, بالايكويشن 2 في عنا plus T1, بالايكويشن 4 في عنا minus T1 و plus T2. And so if we sum up all of them we can get rid of T1 and T2 بيبقى عنا بس الفريكشن. الفريكشن بنحطها بقيمتها اللي هي half MA. We end up with the value of A. So let's do it. انتوا طبعا ما قاعدين تشوفون كلهم بس when we write down all of them you will see. إذا مش بنعمل 1 plus 2 plus 3 plus 4 will end up with so first equation is minus T2 plus mg. So we end up with minus T2 plus mg plus equation 2 بتعطينا okay T1 minus F so plus T1 minus ما انه الاف هي قيمتها half MA رح حتى دغري minus half MA اوكي بلس 4 حطينا استعملنا 1 2 3 وبعد ناقصنا بس ال 4 so plus T2 minus T1 is equal to 1 over 2 MA plus من تاني equation MA ومن أول equation MA so 1 over 2 MA plus MA plus MA وهلا فينا نعمل كل ال simplification so minus T2 plus T2 they cancel out plus T1 minus T1 also they cancel out and so what we end up with بالأخير هو MG من أول وحدة is equal to minus 1 over 2 MA بتنتقل لتاني جهة بصير في عنا 3 MA and so again we reduce the mass factor so we end up with A that is equal to 1 over 3G and this is the answer this is the acceleration we are looking for this is the acceleration of the block A. This is it for the second equation. For the second question اللي هي كانت جيبوا الاكسلريشن للبلوك. Now you have to deduce the tensions T1, T2 and you have to deduce the magnitude of the friction F in terms of M and G. طيب فإذا هون بتالت question صار في عنا what are the expressions of T1, T2 and the friction force as a function or in terms of the mass M and G. Okay, that's quite easy. Let's start with the easiest one. Equation 3 بتخبرنا have a look. Equation 3 كانت تعطينا ال F as a function of A. So I will write down equation 3 F is equal to 1 over 2 MA. So it's 1 over 2 M times 1 over 3 G. And so we can deduce that the friction force is given by 1 over 6 mg. هي بالنسبة للفريكشن. Now, what about T1 and T2? Let's have a look. T1 and T2 فينا نجيبهم من equations 1 and 2, possibly, yeah, or من equation 1 and 4, for example. So let's deduce first the value of T2, for example, and then we can deduce then the value of T1. So we have equation 1 بتعطينا, equation 1 we can write down, minus T2. Oh, T2 مباشرة is equal to the mass multiplied by G minus A. So it's equal to M multiplied by G minus 1 over 3 G اللي هي 2 over 3G. So we end up with 2 over 3 mg. And so this is the value of the tension T2, right? And then at the end, we still have to deduce the expression of T1. طيب من equation 4 في عنا T2 minus T1 is equal to 1/2 MA. So we end up with T1 equals T2 minus half MA. So T1 is equal to T2 minus half MA. So it's equal to 2 over 3 mg minus 1 over 6 mg. And so we end up with 4 minus 1, 3 divided by 6, 2. So we end up with 1 over 2 mg. وبتطلع معنا هيدي هي الفاليو ل T1. So this is it. We have expressed and deduced the expressions of T1, T2 and the friction force in terms of the two only variables اللي هن ال M, the mass of the cylinder and the mass of the block واللي هي نفسها الماس of the pulley and the gravitational acceleration G. So this is it for the part C, and finally in the part D اللي هي آخر part بهذا ال problem كانت. In part D you had to use the conservation energy approach to find the speed of the block B after it descends a distance D. فإذا إذا البلوك B نزل distance D أوكي هون إذا هذا البلوك قدر ينزل through a distance D, so from this point it goes down to this distance D. What is the speed? What is the speed of the block لما صار بهالنقطة هيدي؟ قد ايه بأي سرعة كان عم يمشي؟ So using the conservation energy approach, obviously we will use the conservation of the mechanical energy because this system is conserved and there are no non-conservative forces that are working in this system. وبالتالي there is no transfer of energy into thermal energy, right? This is why we only have conversion of the energy يعني transfer من الكاينتيك للبوتنشال من البوتنشال للكاينتيك. بهالحالة في عندنا transfer من البوتنشال للكاينتيك لأنه البلوك خسر potential energy هو ونازل وهالبوتنشال energy تحولت لكاينتيك energy of translation. طبعا عم بحكي عن البلوك انا بس هذا الشيء لازم ياخذ بعين الاعتبار كل الكومبوننتس لهالسيستم. So this is why let's write down. We can apply the principle of conservation of mechanical energy into this system. To this system, principle mechanical energy to the system, which is composed of the cylinder plus the pulley plus the block all together. And so we can write down the mechanical energy in the initial time is equal to the mechanical energy in the final time. So in the initial time when the system was released and when the block was released first. So the kinetic energy in the initial state plus the potential energy in the initial state is equal to the same summation of kinetic and potential energy in the final state. If we take the gravitational potential energy in the final state to be if we take the level يعني تبع final state to be our reference, then بتصير هيدا صفر. والkinetic energy in the initial state is equal to 0 because we have system at rest. It wasn't moving. And so we end up with U initial is equal to K final. Now, how much is U initial? U initial هي بس the gravitational energy of the block. لأنه سواء كانت البولي أو السلندر, البولي is fixed. ما عندها gravitational potential energy. It's not moving along the Y direction. And the cylinder, it's true that it's moving, بس هو كمان ما عم يمشي along the Y direction. هو بس عم يمشي along the X direction. وبالتالي there is no variation of the potential energy of the cylinder. وكمان بالنسبة للبولي واقفة مكانها, ف there is no variation of the potential energy of the pulley. And so if we take this to be our reference for the gravitational potential energy هيدا الليفل, رح يطلع معنا انه بس البلوك صار فيه variation للpotential energy من initial state للfinal state, and that is equal to m times g times the distance d. So هو قلنا distance capital D. And so U initial is equal to m times g times d. That is equal to. Okay, and in other words, بس لحتى أكون دقيقة أكتر. Let me just حط كل التفاصيل. So في عنا هون U initial لcylinder plus U initial for the pulley plus U initial for the block. That is equal to K final كمان لكل السيستم, يعني عمليا K final for the cylinder plus K final for the pulley plus K final for the block plus U final for the cylinder plus U final for the pulley plus U final for the block. اوكي, هيدا بالتفصيل كيف اشتغلنا. وهلا قلنا انه سواء البولي او السيلندر اثنيناتهم ما عم يتغير الفيرتيكال بوزيشن اللي لهم, وبالتالي اليو انيشال البولي is equal to U final pulley واليو انيشال cylinder is equal to U final cylinder. بس البلوك هو اللي عم يتغير البوتنشال انرجي اللي له بحكم انه هو كان عم يمشي تحرك على الواي دايركشن. and so اذا كانت هيدي هي ايكوال لزيرو فبيبقى عندنا انه اليو انيشال هي الام تايمز جي تايمز دي. اوكي, now what about the kinetic energy? بالنسبه للسيلندر, السيلندر هو عم يعمل two type of motion. It's at the same time rolling السيلندر and it's rolling, so it is it's making a translation and the rotation. And so we can write down K final of the cylinder, it's given by half I of the cylinder with respect to its center of mass, omega cylinder squared, plus half times m times v c squared. وهون by vc squared نقصد the speed of the center of mass of the cylinder، لأنه هون عم يعمل rolling. اوكي هيدا rolling motion of the cylinder C. Now what about the pulley؟ البولي هي عم تعمل pure rotational motion. فإذا the kinetic energy associated with the pure rotational motion هي half، I would just call it IP اللي هي moment of inertia of the pulley with respect to the axis passing through its center of mass times omega p squared. Plus for the block the kinetic energy is a pure translational kinetic energy, so it's half times m times v of the block squared. Okay, now let's substitute كل شيء بقيمته. So we end up with, okay, we have the following. mgd is equal to moment of inertia of the cylinder with respect to the axis passing through its center. It's given by 1/2 mass of the cylinder, radius of the cylinder squared. الأوميجا للسلندر بأنه السلندر عم يمشي السنتر اوف ماس اللي له ب في سي وهو عم يبرم without slipping، معناتها انه الفي سي is related to omega c لانه في عندنا rolling without slipping، ففي سي is equal to radius of the cylinder times omega of the cylinder. وبالتالي الاوميجا of cylinder هي عمليا في سي over r squared، فبصير في عندنا في سي squared over r squared plus half m VC squared. Okay, now plus half the moment of inertia of the pulley اللي هي it's seen as a disk with respect to the axis passing through its center هي 1/2 times m times the radius of the pulley squared. بس ما انه الراديوس r للبولي بالجيفن هو قالوا لنا it's equal to r/2. اوكي فرح نعوضه بقيمتها، نعوضه بقيمته بس مش هلا، خليه على بعد شوي بتاني سطر. multiplied by الاوميجا بي شو بها كمان the cord is moving along the pulley without slipping، وبالتالي فينا نقول انه الاوميجا بي هي equal to او بالاحرى الفي speed للبولي v is equal to r multiplied by omega p، والفي هي نفسها الفي للبلوك، فاذا اوميجا بي هي في divided by r كمان squared معناتها v squared over r squared plus 1/2 times m times velocity of the block طبعا كلها squared. هون ما انكتبت السكويرد. اوكي now what we have to do كمان انه نرجع ننظف شوي نعمل simplification للفاكتورز ونشوف شو بيبقى معنا. So let's move on. r squared and r squared they cancel out, and here r squared and r squared also they cancel out. We can also get rid of the mass term everywhere. فإذا بخلص ال m and m, right? And what else? So we have one more thing to say اللي هي إنه ال V للبلوك هي نفسها ال V للcylinder because the cord is inextensible. So we end up with G times D is equal to 1/4 VC squared. السبيد للسلندر هي نفسها الفي للبلوك، السبيد للبلوك فلحتى V squared plus 1/2 كمان V squared plus 1/4 times V squared plus 1/2 ال VB اللي هي نفسها ال V للبلوك هي V squared. So we end up with 1 plus 1/2, so 3/2 times V squared. And so finally here we can deduce that the speed of the block we are looking for, V squared, is given by 2/3 times G times D. And so we can deduce that V is nothing else than 2/3 GD with the square root. And so this is the expression that we are looking for. هيدي هي قيمة أو قيمة ال V كexpression. And if you have the numerical value for the distance D, then you can just immediately make the numerical application. So the point is, I'll take away message, when you have this kind of system and you want to apply the conservation of energy approach, you have to be careful about what you are considering. And if you consider a given particular object, you have to see if there are external forces acting on this object, or if the whole system is isolated and there are no external forces. If the system is isolated, then you can apply the conservation of mechanical energy. And in this case, it works because the friction force does not transfer energy into thermal energy. فسيحلف في عنا friction force بس الwork تبعها هو صفر, and it's a static friction force. So this is it for this problem.